Hello students, so we begin our 5-week online experience in teaching and learning. Um, what I plan to do is post lots of videos, but also we're going to have online live sessions so that you can ask questions or we can talk about some of the work. And I'm going to be asking you to submit your homework online. You don't have to type it. But I will ask you to send me uh, scanned versions of your homework or uh, your homework where you take a picture of it in a way that I can see it and read it. So the homework will replace the quizzes. Okay, so we have two things to do for the rest of the semester. One is applications of the derivative. So we just use what we already know about the derivative and apply it in different ways. And the second thing we need to do is integration. So we're going to spend a couple of weeks on applications of the derivative, and that's what we're going to start on now. And then we'll move into integration. So what I'd like you to do is consider this problem. You have a function, f of x equals 6 plus x minus 1/5 x squared. Get the tangent line, get the equation for the tangent line at x equal to 5. Now you say, yes, we've done this. We've done this a million times. This is one application of the derivative that we're going to talk about. So what I'd like you to do is shut off the video for a minute and do this problem and then come back. Okay, I hope you stopped and did the problem. Okay, so we need a point and a slope to get the equation for a line. So the point is going to be the point on the curve at x equal to 5. So we need to figure out what the function value is at 5. So at 5, if we put a 5 squared, it's 25 divided by 5 is 5. 5 minus 5 is 0. We're just going to get a 6. So the point we're interested in is 5, 6. Okay. Now we need a slope. The slope is going to be the value of the derivative at x equal to 5. Okay, so we need the derivative. So the derivative of 6 is 0. Derivative of x is 1. Now, let me say something about this. I see many of you using the product rule over and over again on expressions like this. You don't need to use the product rule. Don't make it hard for yourself. It's a constant, 1/5, negative 1/5, times a function. So you leave the constant alone and take the derivative of the function. Derivative of x squared is 2x. So you get 1 minus 2/5 x. Okay. Don't go through using the product rule all the time. This is a constant times a function, not a function times a function. So we don't need to use the product rule. We can use the constant multiple rule. Okay, so now we've got a point. Oh, we need the slope at x equal to 5. Okay, so at 5, the 5's would cancel and we'd have 1 minus 2. So we know our slope is negative 1. One way to get an equation for the line is the point slope form. A lot of you are using that form, and that's fine. I'm going to use it here because your book uses it in this chapter. So we say y minus, the point is 5, 6. So y minus y1 equals slope times x minus x1, if you remember the formula. So notice this comes from the fact that given any point on the line, xy, the rise divided by by the run, y minus 6 over x minus 5 is always going to be negative 1. Okay, now I'm going to go ahead and add 6 to each side. Okay, I'm just going to leave it like that. We could distribute the negative 1. I'm going to leave it like that for now, because there's a certain advantage to that, seeing that form. Okay, so there's our answer. This is a perfectly good answer. Okay, so now we're going to do something a little different with that. I'm going to put that up here. Okay, notice it's just a coincidence that this is a 6 and this is a 6. There's nothing special about that. What we're going to do, one way we apply the derivative, is we use the derivative to get a different form of a function, a form that's easier to use. Now you say, well, but that's already easy to use. We can calculate any value of the function for any x, just put it in our calculator. True. There are, however, many situations in engineering, in higher mathematics, in physics, where you don't want to use the original function because it's so complex, it takes too much computer power, whatever. There's various reasons you don't want to use the original function. But we can use an approximation, the equation for the tangent line. Instead of using the function, when we're near the point where x equals 5, then we're going to get a good approximation to the function using the simple linear formula instead of this formula. Now, instead of using a y, what your book likes to use is an L of x, just to distinguish this from this. This L, linear approximation to this. Okay, so near x equal to 5, this and this are approximately the same. In other words, if we draw a picture, the original function is a parabola going down, and here's the point 5, 6. Here's the line. Okay. So let's say okay, so near, really around here, the tangent line and the function are almost indistinguishable. So instead of calculating values of the function using this hard formula, we can use this. So if I use this, let's say I want to figure out the value of the function at 6 instead of 5. So I'm going to put a 6 in here. And I'm going to get 6 plus, 6 minus 5 is 1. 6 plus negative 1 is 5. Okay. So let me draw this. We're saying that if we go over here, let's say, to, so I'm going to draw a little triangle. We're on the tangent line. So if we go over 1 in x, so our run is 1, our rise is going to be negative 1. And we're going to wind up at 6, 5. Okay. Now, where do we actually land up? If we use the original function, we're going to get 6 plus 6 minus 6 squared is 36 over 5. Okay, so if you do the math, do the arithmetic, it turns out you get 4.8. Okay, so our approximation was 5. That's L of 6. That's our linear approximation. Our actual value at 6 is 4.8. We were off. We were off by how much? Well, 0.2. Let me show you what that looks like on this. So actually, let me draw this a little bit. Actually, the problem is here in the linear approximation we were following the line. If we actually follow the curve, then at 6 we're going to be at 4.8. Not at 5. So we're going down. Okay, so when x goes from 5 to 6, right? The linear approximation took us from y equals 6 to y equals 5. Okay? So when we took x from 5 to 6, our linear approximation took us from 6 to 5. But the actual value goes to 4.8. Okay, so we need a language we need to call these things something. Okay, so let me make some room. We're going to call these ideas something. So we know that when the actual amount we went down in y was not -1, it was -1.2. That's the actual, because we went from there to there. That's the actual amount we dropped, because we went from 6 to 4.8. In our approximation, we went from 6 to 5. So we call this actual change in y delta y. That's the actual change in y. What do we call the estimated change in y? We call that dy. The x change is the same no matter which one we're talking about. The x change is the same. We're going from x equal to 5 to x equal to 6. So we call that delta x or dx. They're the same things. So what we have here so we're saying that if delta x is 1, because we're going from x equal to 5 to x equal to 6, dx is the same. Delta x dx, we call them both the same. But our delta y, our actual change in y, is -1.2. Our approximated change in y is -1. So we call these actual changes, right? These are called differentials. And notice, if we go back to the original function and talk about dy dx, what was dy dx at x equal to 5? It was -1. Okay, so we can multiply both sides by dx. And we're saying that given a change in x, we know what the approximate change in y is going to be. Because that's the slope. That's what the slope is. That's what the derivative is. That's what the slope of the tangent line is. If we stick with the tangent line, if we go, our slope is -1, change in y over change in x, but not the actual change, the differential change. So our approximation is related to these differentials. The actual change in y is actually, if we put in the two values for x we're considering and look at the difference in the function values. Okay, so I'm going to stop here, and I'm going to then come back and do some problems from the text about how we apply all this. What does all this mean? How do we apply it? There's also notes online with your homework assignment. Your homework assignment for this section, let me put that up here. Your homework assignment is going to be chapter 2.9. Numbers 1 to 4, 11, 13, 19 to 22, 23, 25, 31, 32, and 33. I'm going to do a few of these, 2 or 3 of these, in videos that'll follow this. But you're also going to have to write these out and submit this to me online. So we'll talk, and this will all be written up, or this is all written up in the notes for today on Moodle. I'll see you in a minute.